Hello. In this video, we conclude with continuous interest. So by now, you've already kind of learned that you can have a future value amount equal to a principal times 1 plus r over m raised to the mt. This is where basically the r is the interest rate, the m is the period, the t is the years, and p is the principal. So the question becomes, what happens when m goes like to infinity, for instance? So basically, one thing that we can do is rewrite the equation. So we have 1 plus r over m, and this is raised to the m, but I'm going to change it a little. I'm going to write m over r multiplied by rt. Now, here's where it gets a little interesting how I rewrite this. So I'm going to rewrite it in the following manner. 1 plus 1 over m divided by r. And this is all going to be raised to the mr, but multiplied by rt. Now here we can do like kind of like a change of variables, for instance. It really doesn't matter what letter we use as long as we don't get confused in terms of like what does that become. So for instance, like if I was to say that, let's say for example, that x is equal to m divided by r, then in that case you have the following. You have that p is going to be multiplied by 1 plus 1 over x, and this is raised to the x, but you also have r and then t. Now, here's where we kind of get a little hand wavy, where we'll basically say that if this value x becomes very large, so for instance, we have that, and we'll write it like this. If x basically approaches a big value, then you have that the amount 1 plus 1 over x raised to the x will approach the constant e. Now, in this case, e is actually a number that is between 2 and also 3. Now, in this case, most of the time we tend to just say if we do second ln, raise it to the first power, it's 2.71828 and some change. So in that case, that means that we do have an equivalence for e. So or e is approximately 2.71828, and then it just goes on forever because of the fact that it's an irrational number. Um, so in this sense, all that we want is just this number right there. So we then get that basically uh, you have that thus A equals, so A is going to equal to the amount P E R T. So this amount is what we call the future value with continuous interest. So we have that A is equal to PERT, and we'll just say that this is said to be the future value with continuous compound interest. Now, most of the time, you have to look for that word in either case, continuous compound interest for these types of problems. Now, technically, I can solve for, in this case, P. So P would equal to A divided by, let's see, E. So that would be E to the RT but that's the same thing as A equals, not equals, but times uh, e to the negative RT. So in this case, this is like giving me another formula in that sense. So this is essentially, this is the principal value. So this is the principal value with continuous compound interest. Now, in that case, that kind of gives you an idea like what a specific amount might be if we had a continuous compound interest situation, which in more or less circumstances, it's thought of as sort of like a hypothetical, not necessarily a reality, if that makes sense. So, like for example, if we have that P is equal to, let's say, uh, 2500, okay? And then let's say that R is equal to 0.05. And then we'll just say that T is equal to, let's say, 4 years. So basically, we can find, for example, what A is. So A is equal to 2500 multiplied by E raised to the zero point zero 0.05 times 4. Now, in this case, this is going to give us the amount. Okay, so at this point, you should be using a calculator because essentially if you round or you use this value, it's going to get a little messy. So we'll just do second ln zero point zero 0.05 multiplied by 4, and we just hit enter. Now that's 3053 and 51 cents. So 3053.51 cents. Now that's the future value amount with compound interest, mind you. So this is how much was attained. Okay, now consider this, that the interest that was earned with continuous compound interest, so like I would still be equal to the accumulated minus the principal, which in this case you have 3053.51 minus the 2500. Okay, now if I do that, if we do that minus the 2500, well, you can kind of see that the amount that was earned was basically 553 and 51 cents. Okay, so the interest that's earned is 553 and 51 cents. Now, that's kind of interesting as it relates to earning interest if we had a continuous compound interest situation, because then in that sense, you might be inclined to think, well, if something can be continuously compounded, why don't I just do that for every single deposit amount? Because then in that case, that would imply that, for example, that I might actually be forced or able to take an early retirement, for example. But consider this. Let's say that your principal amount that is deposited is, let's say, you're able to put away 5,000. And let's say that for this, that T is going to equal to like 10 years. Now, let's say that we manage to get a good percentage amount. So in this case, like uh, let's say that we have 5.5%. Okay. Now, consider this though. Okay. Now, what if we wanted to explore the amounts that would be earned if it was annual, semi-annual, quarterly, monthly, even daily, And then we can look at maybe like continuous compound interest. So what that means is that potentially we're going to just try to see like how much is going to be earned over this amount of time. So for example, when we have that the amount is annual, well, in this case, all that we need to do is just plug in to our formula. So we have 5,000 multiplied by 1 plus 0.055, but it's annual, so it's going to be raised to the 10. Okay, so we just push enter, and the amount that we have is 85.40 and 72 cents. So we have 85.40 and 72 cents. Uh, Mind you that that is yeah, that's thousands. Okay, so let's say that we go ahead and we find the amount for semi-annual. Now this might take a little time, so that's why I'm going to go ahead and just create a function of which I'm going to do 2500 plus, not plus actually, multiply. So we're going to go ahead and put 1 plus. Now here's where basically you just need to type in the interest, and then the x is going to be the amount, the period. And this is going to be raised to the xt. So we have x and then, well, it's actually done for 10 years, isn't it? So it should be 10x. Okay, so in this case, we can actually go ahead and say, for example, that the minimum is 10. The maximum, we can do 50, for example. And then for the minimum, we'll just do like -1. And then the maximum, we could probably just say like 15,000. I mean, okay, because potentially I think that I might be inclined to think that my amount grew to in a ridiculous amount. So we just go here. Okay, so let's go back to the value of 1. So that's the annual case. Okay, let me see. Mm, Something doesn't seem right. Ah, it's 5,000, isn't it? Yeah. Second enter, so that'll be 5, 0, and then we just delete those two. So we just go to our graph. Okay, so just go back to value. Okay, so we have that 85.40 and 72 cents is the first one. Semi-annual 86.02 and 14 cents. So we have 86 um, yeah, 86.02 and 14 cents. Okay, so that's okay. So it's a little more. Quarterly, let's see what happens. 86.33 and 85 cents. So 86.33 and 85 cents. So this is for the quarterly. Now we can go ahead and look at monthly, for example. And in this case, monthly is just when it's 12. So we're going to type in 12. Now 86.55 and 36 cents. Or is it 55? Yeah, 55. Okay, so 55. Okay, so we'll just do like this, 55. and 38 cents. Okay, now you can kind of see that the amounts, if you look at the differences, it's not by much. You have like it's like $62, but if you look at the interest, like in increments, you'll see that it's not really increasing by that much. In fact, over here you have that it's increased by 22 cents, or $22, I'm sorry. But now let's go ahead and look at the daily. So daily, let's go ahead and assume that our daily period is 365. So, for those that are like kind of wondering where are these numbers coming from? Well, we're doing the 1 plus 0.055 and dividing that by 365, and we're raising that to 365 times 10 because you have that it's done for 10 years. So, you can enter that into the calculator and it's going to give you the exact same thing. So 365, um, yeah, that's because of the window. Um, yeah, okay, so let's do 400 just to do that. Now, we just need to tell it to do 365, 365. And we have that it's 86.65 and 91 cents. Okay. Now, in this case, note that, I can find the interests respectively from each one, but if you look at the differences between each one, respectively, those interests, you'll notice that they're not really increasing by much. So that's something to look at, but you can kind of tell just based off of the initial amounts or the final value amounts that they are increasing, um, not really by much if you think about it. Like this one is $10. Okay, but okay, now what if we were to use a ridiculous amount? So in this case, the um, some people like to call it the PERT. So times 0.055 times 10. Okay, so I just put enter, and okay, so 8,666 and 27 cents. So we say that the continuous, it's going to be 866 and 27 cents. So we see that basically the difference between the daily is not by very much if we think about it, because again, you can actually figure out the increments that these increased by. So like, we take minus the previous amount of 8,665 and let's see, and 91 cents. So we get that it only increased by 36 cents in that case. Um, of course, if you want to find the interest, so like if you look for the interest, so you can actually take the interest by getting the accumulated amount, subtracting the 5,000, and then there we go. So in this case, this tells us that the largest amount of interest that gets paid back is 3,666 and 27 cents. But that's only if it's continuously compounded. So we have that the amount of interest, so I equals to about 3,666.27. This is the largest amount that will ever be paid back hypothetically in that sense. So unfortunately, my plan of becoming a early retiree what doesn't exactly work out. So in this case, Yeah, you would have to basically just either make a larger deposit or make the or just let more time pass by, like instead of 10 years, maybe do 20 years. But one thing to consider, if you look at it like this, like if you know that there's 365 days and you know that there's 24 hours, okay? So, if you were to do this like by the minute, so, there's 365 days times 24 hours times 60 minutes times 60 seconds. This is the number that we could possibly try to put into the calculator. So, like, for example, like 5,000 multiplied by 1 plus 0.055 divided by this number right here, and then we just close it. We raise it to that same number, and we multiply by 10. Now, this is depositing or compounding our amount per second, basically, for 10 years. But see, like how we see that our answer, it's not very far off from the initial. So, like, we got that it was 866 and 27 cents. So we see that the difference is not really by much in this case. So we can see that even if we were to go even faster, for instance, like every like millisecond, then in that case, it's still never going to exceed this amount of 3,666 dollars. Okay. And then completely, this is obviously a hypothetical. Especially like if you were to graph the equation. If you graph the equation, I mean, it gets a little misleading because then you have that amount, it kind of might you might accidentally look at it like that, like you have y equals p times e to the rt, and the equation looks like this. But in actuality, it's going to be approaching a very small value in this case, which we found it. It's 8,666 and 27 cents in this case. Um, or just look at it like that was the largest interest amount that was paid back for that. Now, if anything, the only thing that you would need to do, for example, is to know like which one is which. So, as you're gonna wrap up this chapter, you just have to know that there's simple interest, which in this case you have that's going to be the accumulated is equal to P times 1 plus RT. Okay, so this is simple interest. Now, and this is the future value. And then you know that there's the compound interest. Now with compound interest, you have that's A equals P times 1 plus R over M, but raised to the MT, where M is just the period. But then you also have that there's for continuous. Now for continuous compound interest, basically you have that it's going to be where A equals P E R T. Now, for these respectively, these are the future values, mind you. So don't get confused in terms of like, what if I want to solve for p? We'll just divide. What if I want to solve for p? We'll just divide, and same thing, just divide. So those are those formulas respectively. Now, the other thing of which that you do look at in this section, just to kind of wrap up this section again, is that you will look at what is called effective interest. Now, whenever you look at effective interest, basically you're only looking at either two cases. You're either looking at that you take the let me see. Mm, you take the 1 plus the r over m and you raise it to the power m. So in this case, it's looking at the effective interest over just 1 year. So in that sense, like we don't really look at the principal amount because technically we wouldn't need to look at it in either case. Um, Now, the other possibility is that you would be looking at the amount e to the r, and then that's minus 1. Yeah, it's minus 1, sorry. So basically, it's either of these two formulas. So, like, for example, if you have that something is compounded at an interest rate of, let's say, like 4.2%, and that this was done for 12 months. Basically, you would be plugging that into the equation uh, for effective interest for compound interest. So you have like 0.42 divided by 12 raised to the 12 minus 1. Now, of course, this will give you the following. It'll give you 1 plus 0.042 divided by, oh wait, let's do this. 1 plus 0.042 divided by, let's say 12, and then we just raise that to the 12, right? And then just subtract 1. Now, we see that basically this gives us 4.3%, which technically isn't really that great when you think about it, but it should always be greater. So you have that it's about 4.3%. Now, most of the time, especially like if you work in retail, usually you call this the APY, which is the annual percentage yield, or the APR. So in this case, like you would get 4.3%. Now, if this was continuously compounded, however, that would be a bit different. You would have that you would have taken the E and you would have raised it to the 0.042, and then you just subtract 1. Now, in this case, this is only if the amount is continuously compounded. So in that case, it's an entirely different effective rate if you think about it. So like 0.042, and then you just subtract 1, and uh, well, as it turns out, you get more or less the exact same thing. Um, yeah, so you more or less get the exact same thing. In this case, it's going to be about the same. Now, you have that that's going to be 4.3%, but that's for compound interest, by the way. It may be more useful to just try it with a different number. That way you can kind of uh, see like better examples because in this one it came out to be more or less the same. Um, but it really just depends, to be honest, like what the scenario actually is. Because I know that like if I try like 5.5%, I can probably just compare it. So like, like if it was like 0.055 and it was done quarterly, and then I just raise it to the fourth power and I subtract 1, I see that it's 5.6%. So in this case, there is a small percentage yield, but it's not like, an enormous amount, which of course, like if you do the continuously compounding and then you just subtract 1, you more or less are getting the same thing, but in this case it's 5.7. So this one's a better example because the annual percentage yield is a little higher for this case. But that's because of the fact that the M was smaller uh, than, doing it quarterly. So in this case, you would have that these two are close together because of the fact that M is actually as much as it can be for that 1 year, mind you. Well, I guess you could do daily. Okay, so another case, like this is the conclusion of your first section on the mathematics of finance. In the next section, you're actually going to be looking at some examples of future values of annuities or present value of an annuity. You can think of it like kind of like money that's saving or money that you're borrowing.